Hi, welcome to CB2330, Foundations of Scientific Computing for the Life Sciences. This course is taught by me, Ian Hoffecker, through KTH Royal Institute of Technology. I'm a researcher in the Department of Gene Technology at KTH, and the goal of this course is for us to review and solidify the basic tools of the scientific process that are needed to conduct research in the 21st century. In this video, I'll cover what our goal is when it comes to what we want to learn here and roughly what our approach and philosophy will be. Scientific computing is an essential skill for all life sciences, and in this Venn diagram here we can see that the modern life scientist must possess a skill set that is at the intersection of computing and engineering, health, medicine, biology, and mathematics and statistics. This diagram also mirrors one of the challenges of teaching a master's curriculum in modern science, which is that it's interdisciplinary. Some of you may have a background in one of these topics, but may lack knowledge in the other. Our goal in this course will be to anchor us to a common language and a way of approaching science. My decision for our approach is to focus on probability and statistics and their exploration using computing tools. To connect this to the life science aspect, we'll try to use these tools to explore datasets and problems that are common across modern life sciences. I intend for this course to be mostly a kind of review of ideas that you most likely have already had some exposure to. Review is something that I think is really important, and a lot of times when we learn something like statistics or probability for the first time, we're so focused on understanding the basic concepts that we don't have the mental bandwidth to connect it to other things we care about. So I hope that this familiarity you probably already have, most likely having seen things like histograms or probability distributions before, that this will allow you to take the further step of absorbing that knowledge deeper into your modes of thought and to help begin to cultivate a kind of scientific identity and to start thinking of yourself as a quantitative thinker who is fluent in the logic of science. So if we go back 100 years, people used pen and paper or slide rules to compute things, and the consequences of this were that certain scientific concepts were not possible to explore in those days. When we look at life science and biology, we're immediately overwhelmed by the complexity and scale of the subject, and biological data is often so large that and so multidimensional that our human minds cannot comprehend it. So we need tools, we need methods to augment that comprehension so that we can actually deal with those numbers. If we look at some of these numbers, so we have 10 to the 4th power coding genes, 10 to the 9 bases in the human genome, 10 to the 5 mRNA molecules in just one cell. And then if we consider our own brains, how many objects can we hold in our working memory? Say if we're doing mental arithmetic, it starts to get hard around 4, right? But large numbers are what computers are, of course, good at handling, and that's why today we're in the middle of a kind of scientific revolution in life sciences. And this started a bit later than the scientific chemistry revolution, let's say, or the physics revolution that happened in the early 20th century. And so things took a while in our field to get going because computing technology and computing competence needed to exist first. But combinatorial complexity is going to limit what we can get by brute force. So there are limits to what computers can do, right? In a biological science context, we have to deal with combinatorial complexity. If we take a small-ish 100 amino acid protein, that's going to be 20 to the 100th power, or 1.3 times 10 to the 130 possible sequences that we can form from that using an alphabet of 20 amino acids. And to put this in perspective, there are only 10 to the 80 atoms in the universe. So this means that while we can use a computer to brute force enumerate through all the possible moves in, say, a game of checkers, or a short nucleotide barcode, or some small chemical molecules, we'll never be able to do this for some of the most trivial types of biological subject matter that we're certain to encounter. So the fastest machines today can compute at a rate of 2.2 times 10 to the 18 operations per second. And this means that it would take something like 10 to the 100 years to enumerate the 100 amino acid sequences on this machine. And again, for comparison, the age of the universe itself is on the order of 10 to the 10 years. So if we conduct scientific research in life sciences, we're faced with these numbers, and we have to perform a kind of balancing act where we're always trying to apply our computational firepower, but where it can do the most useful work. And scientific computing in the life sciences is therefore a matter of making strategic assumptions, applying reasonable constraints to problems, relying on sampling methods, for example, to obtain representations of a phenomenon rather than exploring it exhaustively, or projections, projecting or predicting a system's behavior in the absence of direct evidence. So in this course, we're going to explore scientific computing according to four, let's say, basic pillars. And the first one is modeling, so formulating a problem in a useful way that's amenable to computing methods. And the second is applying numerical methods or algorithms to put our machines to work. The third is using our models and machines to simulate or generate data that we would otherwise have to gather through more difficult real-world experimentation, and operating instead, in a kind of abstract space. And fourth, we shouldn't forget, is validation. So this lets us then loop back to the beginning after we see that our model may have captured some features, but perhaps missed others, or failed in certain ways that experimental data may have revealed and now needs to be addressed. So let's take a closer look at each of these. So if we go to the first one, mathematical modeling and problem formulation, usually a model starts with a basic mental conceptualization of a phenomenon. So we have some mechanistic idea of what's driving a certain process, and or a hypothesis, let's say. And let's take the example of growing a population of bacteria. And so with each division, we have some chance to introduce a mutation. So we get a resistant mutant that arises, and which then starts its own lineage of resistant individuals. And in this step, we've done the conceptualization now. So we have this process that we care about. And now we might ask a question like, how many resistant mutants do you have when we decide to harvest after some time? So then next step is to select a modeling approach, a modeling framework. So the specific mathematical framework that we use to describe our conceptualization, should capture precisely the aspects that we care about. So, for example, a deterministic dynamic model, for instance, would have us write out a dynamic equation representing the relevant process variables and their rates of change. We might use a numerical solver to step through that equation discretely, or attempt to find an exact solution, an analytical solution. Or alternatively, we might select a stochastic modeling framework in which we describe our number of mutants with a random variable, and with mutations occurring each division with some probability. So a single step in this approach might use a random number generator to decide whether in a specific instance a mutant occurs. And if we were to plot the trajectories of the two approaches, the stochastic approach gives us multiple possible trajectories or distribution of possible versions of reality, whereas the deterministic dynamic equation approach gives us a single value. So which modeling approach is more useful to us might depend on what scale we're working at, if there are tens of bacteria or millions of bacteria. But in going through this process, we've taken this conceptual picture and established a couple mathematical descriptions that mirror that initial mechanistic understanding that we had in our minds. So next we go to numerical methods and algorithms, and in this case, so we have our model now, and what we want is to get an answer out of it. And although we were able to formulate a precise mathematical description of the generating process underlying our phenomenon, this is not the same as having the answer. So today we're almost always putting machines to work in order to find those answers. And in many cases, we're relying on numerical methods as opposed to symbolic algebra, for example, because machines are well suited for this type of work. So if we continue with our bacterial mutant example, we have an analytical expression, and by the way, this growth term here we can substitute with a simple model of exponential growth for bacteria. So this is where the rate of change of bacteria is proportional to the current number of bacteria. And if we want to evaluate this model, which is to compute the number of mutants that occur after some time, we can use a numerical algorithm that discretizes time into defined steps of time, and we compute the change each step in the number of bacteria, which then determines the overall growth rate, and in the number of mutants, which is based on this number of bacteria. So this might look something like we start with an initialization, and we establish starting values of the bacterial and mutant population, and then the rate constant, the time step, etc. And then we step forward in time. So first computing a new value of the mutants, and then a new value of the bacteria. And then we loop back multiple times, say 100 time steps, to obtain an estimate of how many mutants we expect to have after some time. So this is a kind of projection where we use the machine to carry a rule forward. And in this case, the rule was easier for us to design, but we needed the machine to obtain the projection based on that rule. So then we go to simulation and generation. And so sometimes mathematical formulation is difficult, right? So we may lack the insight or ability to produce a neat analytical formula that's describing the phenomenon we're interested in. So maybe it's too complex, or there are maybe too many moving parts to allow us to isolate just a couple variables. But sometimes in these situations, we're still able to simulate the process. In the same way that we can conceptualize that process mentally, we can build a system with programming that mimics that process and uses computational operations to project that behavior. So a simulation might look something like we have a number of bacteria and we have a number of mutants to start with. We store those as variables. We conduct a loop in which each bacterium gets a chance to mutate. So this is sort of like flipping a coin. But on the computer, we use a random number generator. So we generate a result that's probabilistic. And we conduct some number of doubling times, let's say. So each loop, each iteration, the population of bacteria doubles. Any mutant populations also double. And then we also keep track of how many wild types turn into mutants. So in this way, we capture the behavior of the system according to this mental conceptualization that we had. So we have a rule that makes sense to us, and we implemented it from the bottom up in the code. And we simulated that behavior without relying on some knowledge of what an exponential growth formula looks like, for example. So this is again an example of a stochastic model. So if we run this program, we'll get different versions of this for different random number generation instances. And only if we repeat this simulation many times do we start to converge on the average behavior. And we'll discuss later why this is the case, but the error or deviation from that average behavior, this is going to fall according to the square root of the number of runs that we do, the number of repeats. So this means that there are diminishing returns, and we'll only ever approach the answer, so we'll never arrive at it exactly. But the power of this approach is that we got an answer to begin with, and we did it without this top-down perspective of understanding what the system dynamic equation that was required for this analytical approach. So all we needed was the bottom-up understanding of how the system behaves in one step at a kind of individual level, and this was enough to approximate the behavior. So then the last pillar, validation, inference, and interpretation. And often we'll have a data set, and we then want to pair it with a mathematical model. And what we want to do is parameterize that model. So this means fitting the model and the data so that we have parameters that produce a model outcome that matches the data. And we do this by systematically modulating the parameters of that model. So when the model and the data are in agreement, we've obtained a set of parameters that we think therefore are relevant to these experimental conditions that we're working with. And in this way, we've connected now our initially abstract model, now we've connected it or grounded it to physical reality. And what we can do is flip things around. So we can go the other direction. If we have a set of parameters that we trust, we might then use this model to generate data or make a prediction that we don't have direct experimental observations for. And validation might involve taking those predictions and comparing them with some corresponding real data, or maybe we've set some data aside for validation purposes. And the goal here is to see, was the model able to, did the model hold up? Did it generalize beyond its training data to predict something that we didn't observe? And the classical example is fitting a line function. So to do the fitting, we change these parameters of the line function, the slope and the intercept, and we do this until the residuals or the difference between the model and the data are minimized. A common trade-off we'll encounter is this tension between a model that is under versus over specified. So for example, if we add too many parameters, like as many parameters as we have data points, then the model is not adding any ability to generalize. And but some processes can't be described without some minimum number of parameters. So a principle in scientific computing is often to apply something like Occam's razor, or a normative approach, which says that the best model is the simplest one that you can get away with. So scientific computing has these basic elements, and this is too big a space for us to really cover everything, obviously. So what we're going to have to do in this course is to focus on what I consider to be one of the more useful frameworks for scientific computing, and this is statistical computation. And the reason this is useful is because science is inherently full of uncertainty. So anytime we take a measurement, we're going to have experimental error, noise, and so everything we look at in science can be thought of as some kind of random variable. And this is true in life sciences, but also in physics and chemistry, etc. So statistics gives us this rich lingua franca, this rich language for modeling and understanding and interpreting scientific data across disciplines, and various objects like distributions or estimators that make studying a subject possible systematically and in a way that lets you dissect it. These will be the goals, the objects of our investigation. And computing machines are the tool for conducting this exploration. And a framework that we'll use in this course is the probabilistic model. So this is represented here as this conditional probability statement, which this is saying here, this is the probability of some observation or data x given a set of parameters theta. And this turns out to be a useful way to explore these four pillars of scientific computing that we've described. So one, for example, first chooses a form of P as a model, a distribution. One can evaluate P numerically. Often there aren't analytical solutions available. One can use a probabilistic model to sample from and generate simulated data. And one can use experimental data to search for theta, the parameters, and ask if the model P was correct. So we'll go through all this again, so no need to worry. And the idea in this video is to give you a taste of what we're going to be doing in the course, and I've essentially given you a preview here. So I just want to end here on a final comment about our approach and philosophy. A lot of statistics knowledge in our education has been hard to absorb because we haven't had the benefit of experiencing it and using it for something important. And many scientists, myself included, didn't really begin to grasp these concepts until we needed them for work. And in my experience, having a project and being forced to build things with programming, in this case, this is the best way to understand mathematical concepts. And the process forces you to experience, different angles, different aspects. You get this kind of satisfying feedback loop where maybe you generate a nice looking plot, or you obtain a result that informs you of what the system or equation is doing. And so our philosophy in this course is going to be really to try to bridge this gap between mathematical understanding of analytical equations and closed form solutions, etc., to this kind of raw intuition that you get when you build things, when you do programming in a way that captures the dynamics of those equations. So what do you think? Is scientific computing an intersection between classical computing, mathematics, and life science? Or what is scientific computing in the life sciences to you? What do you think is special about life science? How might it differ from other fields of science, and how does scientific computing differ between these? What kinds of skills and knowledge do you think you might need to be able to conduct professional, modern scientific research in this century? And what are the skills and knowledge that you believe are the most enduring and that will still serve you well in 10 or 20 years?